Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Ever since, for the last 40 years, I've been interested in stream processing. And you very likely have seen the example I'm going to talk about today. It appears in Abelson and Sussman. I've published it in more about it in 1990. Kaczmarczyk in France has written about it extensively, but it keeps getting better and better over time. And this is the manipulation of infinite data structures, infinite lists in this case, and in particular, a beautiful example of infinite data structure is power series, which is just a stream of coefficients. Knuth Volume 2 has a chapter on power series computations, and he talks about two kinds. And one of the kinds is what you'll get if you do power series in Maple, or I think it's still the case that in Mathematica, that you decide in advance how many terms you're going to get and then deal with polynomials. And the other is the online algorithm, where you compute terms ad nauseum until you get tired. And it's that I'm going to talk about today. This depends critically upon lazy evaluation. That if I'm going to add two power series together, I cannot do call by value. It would take a little while. And these properties will become clearer during the talk, will become illustrated during the talk. Conceivably, with a fairly small audience, everybody's written in Haskell code. No? All right. I'm using Haskell, and the reason I'm using it is more beautiful for these particular algorithms than anything else I have ever seen. Haskell actually, way back when, it was said that Fortran looked like mathematics. But in Haskell, this is often very true, and it's sometimes the Haskell guides the math rather than vice versa. And that we'll see today. So, in Haskell, really fundamental operator. If you know Lisp, this is the const operator. It takes two arguments. The first argument is an item, and the second is a list of items, and it tacks x on the front of a list of x's. And functions are defined by pattern matching. So the tail function, the tail of something which has the form of a const, is simply the second item of the const. The pattern matching also is nice. That's the way we define things in mathematics texts. This tail function is polymorphic. You don't have to know the type of the elements in the list. You only have to know you're working on a list. And I'm not going to talk much about type signatures, except to say here, Here's an arbitrary type. That's a type parameter A. Tail takes first argument, which is of an arbitrary type, a second argument, which is a list of elements of that type, and returns a result, which is a list of elements of that type. That's the cons operator. The tail operator simply takes a list of elements of some type and returns a list one by beheading it of elements of that type. Here's a trivial example of lazy evaluation. The function repeat takes an element and tacks it on the front of repeat of x. This is obviously a recipe for infinity. Just goes on forever. What? And it's procrastination. When you evaluate the cons operator in here, you simply create an empty cell. And you don't put anything in it until somebody wants to look at the contents of the cell. Instead, you put in a recipe for where to go if you need to fill the cell in. That's lazy evaluation. Here's a trivial function of no arguments. What's it do? Produces an infinite string of ones. Now, if I ask to print it, here's the example of you better not call by value. The print function is going to say, give me the next character, give me the next character, give me the next character. And give me the next character will say, when it's a list, fetch the first thing, convert it to a character, fetch the next thing, convert it to a character. And here's a standard Haskell function, take 10 from the list called ones, and this will print the first 10 ones. None of this would go if Haskell were not a lazy evaluation language. Here's a less trivial example. The Phillimore sequence was defined in the early 1900s as an example of a non-periodic sequence that contained no cubes. You can find no sequence of substrings x, x, x for any substring anywhere in this infinite sequence of zeros and ones. And one definition of it is it's a sequence of zeros and ones. It begins with 0, and it's the interleaving, and it's the fixed point of interleaving the sequence with the complement of the sequence. So here is the sequence. Here it is spread out. Here's its complement spread out. And you notice the sequence itself is gotten by interleaving these two copies of the sequence, the copy of the sequence with a copy of its complement. And here's the code. First of all, we have to tell it how to interleave. We interleave a sequence with another sequence, and we don't even care the form of the second sequence, by first outputting the first element and then interleaving the second sequence with what remains of the first. Complement, here's a different kind of pattern matching. You can put constants in the patterns. If a sequence begins with 0, its complement is 1, followed by the complement of the rest, and so on. Now, here's a recipe of our fixed point definition, but it doesn't talk about how to get started. And furthermore, it uses exactly the function. It defines the function exactly in terms of itself, and that's not terribly useful. But if we unfold the definition of interleave one level, we get this formula. We interleave, we put in a 0, and then we interleave the complement of the sequence with the tail of the sequence. And that is working Haskell. This time we've fed the output back into the input, which is something we couldn't do if we didn't have lazy evaluation. We need the first term before we can compute the second term. Now on to power series. Power series is simply a sequence of coefficients. And I'm not concerned at all about issues of, this is formal manipulation, nothing about issues of convergence of sums. Here are some power series. Here's the series which is just the constant one. And putting something in brackets means make this into a series. Make this into a list. 0 is even simpler. It's the empty list. The identity function, which is the monomial x, is a 0 constant coefficient, a 0 constant term, and 1 for the first power term. And then finally, a familiar, the power series for cosine, 1 minus a half x squared plus 1 over 4 factorial x fourth, and so on. We'll see later how to define the cosine really, really compactly. Okay, some of the algorithms are really easy. To add to power series, well, we give it a base case how to handle the empty list. If we want to add 0 to a power series, we get the same one back, 2 ways. And now if we have 2 non-empty power series to add together, we add the first terms, and then we do a recursive add of the rest of the sequence. This is legitimate Haskell. I can define plus this way. I have to do a couple of little tricks, which I'm not going to show because they're crabby and not worth, and something you get from a manual, not something I want people to take home. You can place any data type in a type class. The type class num is things that can be added, subtracted, and multiplied. The type class fractional is things that can be divided. So we'll put strings of numbers into type class num. Lists of numbers into type class num, and we'll put them into type class fractional, and then we can define what these operations are on the sequences in terms of what they were on the scalars. To negate a power series, negate the first term, and then apply the negation operator to the rest. Subtraction is already predefined. It can be defined in terms of addition and negation. Now we get to multiplication, which is more fun. A power series is a sequence that can be thought of as a sequence of coefficients of powers. Or it can be thought of as a first coefficient plus x times the unknown times a power series. And this representation is where we get what is the starting point for all of our algorithms. So to compute the product, we write f as in this form, G in that form, multiply it out, and you will find we can actually collapse this term and this term into FG, this term and this term into F bar times the original series G. And here we've just taken this formula and copied it down here. To multiply by 0, we get 0, if that's what these two lines say. And this says, if we have a string GS whose form is G is given this way, so we have names both for the whole series and for its parts, then the result of multiplying is the product of the first coefficients plus the tail of the series, which is G bar, and the tail of the series was called GT here, times a series of only one term, which is the head of F. And finally, the tail of F times the whole series G. And there it is. Compare it with the formula we always used in freshman calculus for multiplying two series. It's a rat's nest of subscripts and superscripts, and they've just vanished. This is cleaner than the classical mathematics. And it works. That is the whole program for multiplication. Without explaining, without deriving, here are some more. Division, this formula, first, if both series begin with 0, you can throw the initial terms away. Otherwise, divide the first two, and this is simply a formula for long division. Really compact. Take the reciprocal of a power series. It's 1 over, it's just the constant 1 divided by the series. Nothing fancy there. Haskell also lets us do a little trickery, and this is one line of code that I'm not showing you, to say, here's how to coerce a constant into a new data type. I want to coerce the constant 1 into a power series. I'll tell it how to do that. Of course, this is the way you do it. But I can hide it under the rug by telling Haskell, when you see a constant where a power series is needed, make it into a list of one term. And then I can write this. Looks even more like mathematics. Now comes composition, f of g of x, substitution of one series into another. I'm going to use the sharp as a substitution symbol. And the answer is very, very short. However, there's a funny thing in here. The series I'm substituting had better not have a constant term. If it did, that constant term would get substituted into the x squared, the x cubed, and I would have to, in order to evaluate the first term of the result, I would have to add an infinite series by requiring that the substituted series have a 0 constant term. I avoid that disaster. And finally, there's been a whole lot of literature on the subject of reversion. How do you find the functional inverse of a function given as a power series? How from the power series of sine can you find the power series of arcsine, for example? And here is the trivial code. In Knuth, the same code appears in a dense half page of pseudocode. It still has to be converted into an ordinary programming language. And here it is as a one-liner. It's a real testimonial to this particular style of doing business. There's feedback here. We're taking the result, which is RS, and feeding it back into itself. Calculus is pretty trivial. There's the way you differentiate a power series. Everybody's done it since freshman year. And I'm going to use I could have written the code in 2 lines, but I can write it if I wrote it out fully. I can write it in 1 by using some standard Haskell functions. Zip width. Zip goes down two lists together, performing pairwise this function, which is given as an argument. So I want to pairwise multiply one series, which is the series 1, 2, 3, 4, 5, 6, 7, and this is another Haskell shorthand, times the tail. Notice the F0 has been dropped. So we're going to go down the list of integers and the list of coefficients of the power series, multiplying one together to give a result term by term. So here's an example. If we do the derivative of 1 over 1 minus x, we get 1, 2, 3, 4, 5. Why? Because 1 over 1 minus x, as you recall, is the sum of the geometric series 1 plus x squared plus x cubed. And its derivative is 1, 2, 3, 4, 5. Here's the integral done the same way. This is the integral from 0 to x of, it's a definite integral from 0 to x of the power series. The constant is 0. And here we go down. What did I do? It looks like I got those reversed, doesn't it? I want to divide the series by the integers and not the integers by the series. Sorry about that. Yeah. What?
What's the type of that thing?
Oh, because all right. I'm referring now to way back. I showed you a slide that says x, that the identity is the sequence 0, is the series sequence 0, 1, which I defined as x on an early slide. I should have mentioned that. Sorry about that. Thanks for asking the question. And so once x is a series, then 1 minus x is a series by coercion, and 1 over 1 minus x is a series by coercion again. Here we do differential equations. We know how to. Here are the usual derivative formulas for the sine and the cosine, and they're turned into differential equations with initial values. And from the differential equations, we can derive an integral equation that captures everything. So the cosine is 1 minus the integral of the sine. And the reason I put the X on the end is that the words COS and SIN are already stolen as standard functions in Haskell, and this just distinguishes them. And because, moreover, this is not a function. This is a sequence, not a function. So there's the cosine and the sine, and the exponential obviously is easily written exactly the same way. Here is a way to compute the exponential of e to the f of x. Will exponentiate a series. We do it by noting the derivative of e to the f is f prime e to the f. So we can turn that into an integral equation. Again, to avoid adding up infinite sums, we insist that f begin with a 0. And now all I'm doing is writing this formula down. Y is 1, that's the initial value, plus the integral of the derivative of f times y. And if you took a graduate course or even an advanced undergraduate course in differential equations, you probably met Picard's method of successive approximations to find the power series solution of a differential equation by taking it to one term, substituting that back in the differential equation, which gives you 2, substituting that back, giving you 3, and here is the entire thing carried out to infinity. The word generating function, which we've all met as a generating function, is a formula whose power series representation has coefficients of interest for some sequence. And one of the classic examples is a generating function for the sequence of numbers of binary trees, which is the Catalan numbers. The number of binary trees of size of 0 nodes, 1 node, 2 nodes, 3, and so on. How do we do it? Here's the generating function. We'll call it t. Its coefficients are t sub n, which are the number of trees of n nodes, of distinct trees of n nodes. There's one binary tree of no nodes. So t0 is 1. And recursively, a tree of n plus 1 nodes has 1 node at the root and 2 trees under it, the sum of whose numbers of nodes is n. Now, and this is simply one of them has size n minus j, and one of them has size j for some j. The number of different such pairs of trees that you can make is summation of tj, tn minus j. And you recognize that if you're a subscript person. You don't recognize it so easily if you've been working without subscripts in Haskell. If you're a subscript person, you recognize this as the square. T squared tells the total number, the coefficients of t squared tell the total number of pairs of trees that have total number that have n nodes. And that, as we said right here, is the n plus first coefficient in T. So there's the formula. There's a formula that says the generating function for enumerating trees, binary trees, is 1 plus x times its own square. And that's a working Haskell program. And here I converted it to Haskell. The exponentiation operator came for free in terms of multiplication. We can get fancier. Deal with multivariate power series. Power series in two variables can be regarded as a power series in one variable with whose coefficients are power series. And since I wrote perfectly polymorphic programs, I'm not going to have to do anything in Haskell to allow the coefficients to be power series. All it counts is that the coefficients are numeric. And we've already said that power series are are now one of the numeric types. However, if any of these series were infinite, we would have trouble evaluating the outer series. We would never finish evaluating its first coefficient. So it's probably a good idea for the coefficients to be polynomials rather than full power series. So let's do one. A polynomial is a finite power series. Just stop somewhere. Only it's written with the constant term first, whereas we often write polynomials with the highest order term first. So, if I will remember that the Pascal triangle are the coefficient, the rows of the Pascal triangle are the coefficients of 1 plus x to the n for some n. And the first row is for 1 plus x, next row is the coefficients of 1 plus x squared, and so on. So, if we put 1 plus x times y in place of x throughout this series, the coefficients of y to the n, the coefficient of y to the n will be 1 plus x to the n. And so we do that. Substitute 1 plus x for y, and y is, for x, and x is 0 something or other, 1. Oh, I'm sorry, 1 plus x times, this is 1 plus x times y. The 1 plus x is the coefficient, y is the hidden variable. Do the substitution and run the program, and this is what it prints. Now we used a lot of, we did both the substitution and a lot of coercion. If we just by hand do the substitution and work out all the coercions, here is the two-layer power, the two-layer power series that we're evaluating. There's another approach, and if you're into generating functions, you know about exponential generating functions, where instead of the coefficient of x, it's the coefficient of x over n factorial. If we represent a sequence, if we assume that there's an n factorial in the denominator throughout, then differentiation is really trivial. You differentiate x squared, it cancels the 2 out of 2 factorial and leaves 1 factorial. And so differentiation is simply a left shift, throwing away the first coefficient. Product is easy to do. The tail is the derivative. So, to multiply two series together, the first term, the series consists of its constant term followed by a tail, which is a derivative. The product is a product of the constant terms followed by the derivative of the product of the tail, a derivative of the product of f and g. But this is the formula for the derivative of a product. The first times the derivative of the second plus the second times the derivative of the first. Prime, incidentally, is a legitimate character in a Haskell identifier. This is the derivative is the tail. The derivative is a left shift. The integral is a right shift. Composition turns out to be not very hard. And now the differential equations become really simple. The sine has a 0 constant term, and its derivative is the cosine. The cosine has a 1 constant term, and its derivative is minus the sine, exponential. And the footnote here is actually on the next slide, my error. So this is a working program that gets the Maclaurin form, as I call it, after the Maclaurin series, for calculus. And Rutten actually has advocated this is maybe a good way to address calculus. Completely non-standard as far as tradition goes, but he develops calculus in this form. And here using using the Maclaurin form definitions is another generating function example. The Bell numbers, the number of ways to distribute n objects among indistinguishable boxes. And they have this generating function, which is, because it's an exponential, it's the exponential series composed with the exponent, which is the exponential series minus 1. Another way is to write it this way, just noting the differential equation. And here come the Bell numbers. This is the Rutten reference that I mentioned on the last slide. So, with lazy evaluation, we can do a really neat job of handling these infinite data structures. And the clue is compute a head term, recur on the tails. And my current love in programming languages is Haskell, because it lets you write this really elegant code. It depends, and I have relied on the lazy evaluation, on the polymorphism, so we could do things like nested power series, and operator overloading, so I could say plus instead of power series add. And this particular URL shows how to do power series calculations in 10 one-liners. Or once you add the bit that I suppressed, the little declarative information like how to coerce and how to put things in type classes, you may get up to 15 lines. None longer than what we've already looked at. So that's my story on power series. Thank you for coming. Oh, we can actually watch this go if I'm in luck. You'll have to tell me how to get back to that. There it is. We're in there already. Notice that I've already done one calculation, asked for the first 10 terms of 1 over 1 minus x. And for some strange reason, Haskell decides to print fractions with a % sign instead of a slash. Dirty underwear. Let's do one more. Take 10 of sine x over cosine x. In sine x and cosine x, you've seen the definition. This is running that exact code that you saw. And what's this? This is the first 10 terms of the power series for tangent. Oop. So you can build things very quickly. I don't think I need to show more. I could have said show the tangent series, and it would still be printing on the screen. Thanks, Ken. All right. Thank you.